Hey Year 10s, welcome to This Explainer. Today, we're taking your upcoming 5-week applied learning project and framing it as a kind of giant, fascinating puzzle that we're going to solve together. So let's dive right in. You've got this really fantastic mini project ahead of you called The Science of Sports and Activities. And basically, it's all about investigating the hidden forces behind how we move. Whether you're a serious athlete or just someone who, occasionally throws a ball around with friends, this project uses real movement, real data, and real performance contexts. It's super practical, it's hands-on, and I promise you, by the end of it, you're going to see the physical world entirely differently. So, are you ready to turn a lunchtime activity into an actual science experiment? Even if your normal lunchtime routine is usually something super passive, like sitting down for a board game, for this specific task, you've got to select one physical activity. We're talking sprinting, skipping, jumping, cycling, doing a fitness circuit, whatever gets you moving. What's really cool about this is how everyday physical actions, literally from the way the soles of your shoes grip the concrete to the exact arc of a thrown ball, are absolutely packed with physics, just waiting to be uncovered by you. To make sure you absolutely crush this project, we're breaking it down into 5 manageable phases. 1. Your 5-week mission. 2. Choosing your activity. 3. The physics behind the fun. 4. Plan, approve, and test. And 5. Analyze, conclude, and submit. Let's get right into it. Starting things off with Section 1, your 5-week mission. Listen, the golden thread tying this entire project together isn't actually just a science, it's time management. As Year 10s, balancing your workload is a really crucial skill you're developing, and this project puts you completely in the driver's seat of your own schedule. Looking at the timeline, you've got about 6 to 8 hours of required work to get through. Now hear me out on this. That work needs to be spread out evenly across the first 4 weeks. You're in charge of when you do it, but if you leave all 8 hours until week 4, well, you are definitely going to be scrambling before that week 5 deadline hits. Pace yourself, guys. Do a little bit each week, follow the steps, and you'll find the whole thing incredibly manageable. Now, your absolute best friend for this mission is the student logbook. You've been provided with a PowerPoint file that is specifically designed to be your trusty companion through all of this. Absolutely all of your work, your planning, your research, and your results, they all get recorded right inside this one file. There are blank sections and tables literally just waiting for you. So do yourself a favor, download a copy to your laptop right now, save it somewhere safe, and just build on it as you progress through each week. Never lose your work again. Moving right along to Section 2, choosing your activity. This is where you get to take the wheel. Step 1 is simple. Pick a physical activity. Sprinting, jumping, throwing, whatever you're into. Then, Step 2 is where we take that activity and flip it into a testable physics question. For example, you might ask, how does surface type affect energy efficiency in sprinting? That's a great testable question, because you can literally sprint the exact same distance on grass, then sand, then gravel and concrete, and then measure how your times are impacted. You're just looking for a scenario where you change one single thing to see how it affects another. Okay, so once you've got your question, you need a hypothesis. And no, this isn't just taking a random guess in the dark. You need to predict an outcome using actual scientific reasoning linked to force, energy, or motion. We use a strict if-then format for this. So it would sound something like, if greater force is applied when throwing a ball, then the ball will travel a greater distance because more kinetic energy is transferred to the object. See? It's clear, it predicts something, and it's deeply rooted in the physics. Which brings us to Section 3, the physics behind the fun. So how do we anchor your activity in real hard science for Steps 3, 4, and 5? Well, you're going to need to do a little research into some foundational laws. First up, what exactly is the law of energy conservation? You'll define this right in your logbook and explain where energy starts, where it transforms, and where it gets lost in your specific activity. Then, you'll look up Newton's 3 laws of motion, define them, and pick at least one to explain exactly how it applies to what you're doing. Like, think about it. If a golf ball sits perfectly still on a tee until you absolutely smash it with a club, which of Newton's laws explains that? To actually visualize that energy, you're going to use something called a Sankey diagram, which beautifully illustrates Step 4. You're required to draw one of these to show the flow of energy in your activity. It's really cool. The width of the arrows represents the amount of energy, showing you how much is actually useful, like motion, and how much is just wasted, usually as heat or sound. You literally just draw it out, snap a quick photo with your phone, and paste it directly into your logbook. Okay, jumping into Section 4, plan, approve, and test. This right here is the action-packed phase, preparing for your actual experiment. Step 6 is all about getting your plan together. You need to list absolutely all the materials you need in that logbook. And be specific. Don't just write stopwatches. Write how many stopwatches you need. If you're testing balls of different weights, how exactly are you going to weigh them? Then you'll create a step-by-step experimental method. The golden rule here: write your method so clearly that a Year 7 student could pick it up and safely follow the whole thing without asking you a single question. And to make sure that hypothetical Year 7 student would get scientifically valid results, you absolutely must identify your variables. The independent variable is the one thing you are intentionally changing, like the type of surface you're running on. The dependent variable is what you're measuring, like your sprint time. And your controlled variables, those are all the things you have to keep exactly the same across every single test, like the distance you run, the shoes you're wearing, or the person doing the running.
Now, I know what you're probably thinking. Okay, this all sounds great, but when do I actually do the physical experiment? It's the biggest logistical question for sure, and the answer ties right back to our first section, time management. It is entirely up to you to schedule this during those first 4 weeks. But there is a massive catch.
Here is the crucial catch. You cannot, I repeat, cannot, just run outside and start testing. You absolutely must communicate with your teacher, show them your completed method in your logbook, and get their explicit approval first. Only once they look it over and say, yup, your plan is safe and scientifically sound, do you get the green light to move to a safe area to conduct your tests. Communication is key here, guys.
Once you have that approval, boom, it's time for step 7, conducting the experiment. We want reliable data, so you really need to consider running multiple tests. Don't just sprint on the sand once. Do it maybe 3 times so you can find an average. And record everything. Since your experiment is totally unique to you, you'll create a custom results table using PowerPoint or Excel and slot that right into your logbook.
And finally, we arrive at Section 5, Analyze, Conclude, and Submit.
This is it, the culmination of all your hard work. In Step 8, you're going to take that raw data from your custom table and use Excel to build a graph, giving you a clear visual of any trends. Once you've pasted that graph into your logbook, you'll analyze it by answering a few prompts in full sentences. Ask yourself, are your times getting faster as friction decreases? Does the data actually support your original hypotheses or completely reject it?
Then comes Step 9, your conclusion. Honestly, this is the main thing your teacher is looking at to see if everything really clicked for you. You need to provide a solid answer to your original testable question, but you can't just throw an opinion out there. You've got to prove it by specifically referencing the numbers in your data. And then, the most critical part, link those results directly back to the physics concepts of energy transformation or Newton's laws that you researched back in Step 3. Build a logical, evidence-based argument.
If you just follow these structured steps, dedicate a couple of hours each week, and keep everything neatly organized in your PowerPoint logbook, hitting your Week 5 deadline is going to be an absolute breeze. Before you call it done, just do a quick final sweep. Check every single section. Make sure absolutely no table is left blank, save the document one last time, and upload that bad boy to Compass.
I want to leave you with this final thought as you kick off the project. Once you actually map out these energy transfers and calculate the shear forces involved in your own physical movements, do you think it'll change the way you actually perform them? Because when you truly understand the core science of a sport, you might just unlock the secret to playing it a whole lot better. Good luck with your investigations, Year 10s. I literally cannot wait to see what you discover.